Alright, there's a lot going on in this problem, so let's take a second and figure it all out. This is number 6 from the homework, which we didn't actually do. It's a little bonus. So, a firefighter who weighs 712 newtons slides down a vertical pole with an acceleration of 3 meters per second squared directed downwards. So, first thing to note, this is not 10 meters per second squared, which means that the guy is not in free fall. So, that means that it cannot just be gravity acting on him. If it were just gravity, it would be 10 meters per second squared. Since it's not gravity, not just gravity at least, that means that we have gravity acting downwards and we have something acting upwards. And that is where this comes into play. What is the direction of the vertical force on the firefighter by the pole, which is what this is here. Ignore me as I drop my pen. Since it's less than 10 meters per second squared, the pole has to be slowing him down. So this has to be some sort of friction on the firefighter by the pole, like so. So, now we need to worry about the magnitude of this force. Now this is where it gets tricky. So, we know that from Newton's second law, F net is equal to ma. And here's where the problems start. We don't know A. Well, sorry, rather, we do know A. Hold on, that's not a problem. That's just me being confused. We do know A. We don't know M. We know the firefighter's weight, but that's not the same as his mass. Remember, weight and mass, not the same thing. When we're talking about mass, same on the moon. We're talking about weight. This is something that's different on the moon. It's an important distinction to keep in mind. Also, we know that F net, I guess you would say, is Fg minus Ff. Because we've got these two forces, right? Keep in mind over here. And they're acting in opposite directions. So when we think of the net force, it means we're adding up all the forces, yes, but we need to worry about what direction they're in. Now, since the firefighter is going down, I'm going to make down the positive direction. So his acceleration is downwards, it's positive. Gravity is downwards, it's positive. Friction, upwards, negative. So, let's take a look at what we got here. We know that F net is equal to, oops, step back a second, Fg minus Ff. We know what Fg is. This is his weight, remember? We said this like at the very start of this whole thing. And that, 712 newtons, which is a force we should point out. This friction force by the pole is what we want. We know that the acceleration is 3 meters per second squared, but we don't know what the mass is. So we've got two unknowns right now that we got to deal with. Let us tackle this one. So, what do we know? We know the weight. We know the weight is 712 newtons, right? And we know that the weight of a person is equal to their mass times the acceleration due to gravity, because someone's weight is basically the force of gravity on them. The force of gravity on you, well, if it's just gravity, then you are accelerating at 10 meters per second squared. So that's kind of how that's supposed to all come into play. So, this would tell us that the mass is the weight divided by g, or 712 newtons divided by 10 meters per second squared. We have our handy dandy trick. If we divide by 10, we just swing the decimal over. So his weight is 71.2 kilograms. Good. One thing crossed off of our to-do list. Now let's go back to the big problem. Big problem says we've got F net is equal to ma. We know that F net is the weight minus the friction force, because there again, different directions. We know what m is, we know what a is. We want to solve for the friction force. That is our goal. So, we're going to need to get this alone. We're going to kick it over to the other side, bring this stuff over here. So I'm going to add FF to both sides as my first order of business. So I have FG equal to MA plus friction. And I'm going to subtract MA from both sides. Fair game. Did it to both sides. So FG minus MA is equal to FF. Basically, the difference between his weight and the actual net force, what we're seeing, that difference between those has to be friction. So this we know is 712 newtons. This is 71.2 kilograms. This is 3 meters per second squared. And that wonderful mess is going to be the friction force. And it is at this point that I struggle to do arithmetic, so we will turn to a calculator. Do I believe that? It's at this point that I question my ability to do math. We're going to double check with some parentheses, make my life a little safer. Okay. We're good. It agreed with itself twice. So the friction force, 498.4 newtons, and if we care about sig figs, which, I can go either way with it. We've got 3, so 498 newtons. So, again, big ideas. Looking at this, we identified that it's not just in free fall, so there is another force in play. We identified that the force had to be in the opposite direction because it's working to slow down the person. He's not falling at 13 meters per second squared, as always get like a rocket strapped to his head. I don't. I just did yoga. I'm a little fuzzy still. We remembered that weight and mass are not the same thing. Mass is the same on the moon. Weight is different on the moon because weight depends on gravity. Weight isn't even the same at the top of Everest or at the bottom of the ocean. And then we used Newton's second law, and we solved up for our friction. I would recommend take a look at this problem, take a look at the homework, and take a look at sections 4.1 and 4.2 in your textbook. There are some nice practice problems there. The odd solutions are in the back of the book. Good luck!